Hi everyone, welcome back to the channel. Last week we were introduced to the concept of mixture designs and we treated the first part of the topic, which was on mixture lattice designs. And I promised that in today's video we are going to tackle the other part, which is actually on the mixture centroid designs. So without wasting so much time, let's jump straight into it. Before we go into mixture central designs, I would like to stress on the fact that this is the continuation of our last video. And if you've not watched the introductory part of mixture designs, I will strongly advise you to go back and have an overview of what a mixture design looks like. Briefly, a mixture central design is defined such that the number of distinct points in the design setup is always 2 raised to the power q minus 1. This means that if the number of ingredients in a formulation are q, then the number of runs that you expect to have in such a design is 2 raised to the power q minus 1. If you are formulating a product with 3 ingredients, automatically q will be 3. And if q equals to 3, then you are going to have 7 experiments. This is in contrast with the mixture lattice design, where the number of experiments taking q equals to 3 will be 10. So in a mixture central design, we have 7 experiments, 3 less than the number of experiments had it been you chose a mixture lattice design for your experimentation. This is because in a mixture central design, we already have predetermined points we have to conduct our experiments. The first series of points, they are the single component blends. For example, if you have 4 ingredients in your formulation, X1, X2, X3, and X4. For the single component proportion, it means that we are going to be assigning each of these component proportion 100% of the overall mixture formulation. This means that if I assign 100% to X1, then automatically X2 will take 0, X3 will take a 0, and X4 will take a 0. This is because in a mixture experiment, the sum of component proportion is always summing up to 100%. If you decide to give 100% to X2, then the other 3 components will automatically take a 0, so that it should all sum up to 100%. And that is that for single component blends. The next series of points, they are the binary blends. In this case, you are assigning a half of the component proportion to 2 of the ingredient mixtures. For example, if I assign a half to X1 and a half to X2, then X3 and X4 will automatically take a 0, since the component proportion should always sum up to 1 or to 100%. So the third series of experimental points you have to consider, they are the ternary or higher level mixtures. In this case, the ternary mixture means that you are assigning 1/3 of the component mixtures to each of the ingredients. If I assign 1/3 to X1, 1/3 to X2, and 1/3 to X3, then automatically X4 should take a value 0, such that the sum of component proportion should sum up to 100. If I assign 0 to X2, then X4 will take 1/3. The next series of points, they are the overall centroid. In the overall centroid, if you are having 4 ingredients, it means that Q equal to 4, such that the overall centroid will be the equal proportion of all the component ingredients. And here we are going to have 1/4 plus 1/4 plus 1/4 plus 1/4. And if you sum them together, they will give you 100%. Let us use the same example we used in our last video when we were trying to give a step-by-step procedure how to formulate using a mixture lattice design. And here we are asked to formulate this product using a mixture centroid design. And you automatically have to consider the factor limits. You define the factors and then you consider the factor limits. And when setting the factor limits, they should be set such that the upper limit of each component and the lower limit of the other components should always sum up to 100%. If I consider the upper limit of x3 and the lower limit of x1 and x2, they will all sum up to 100%. The number of experimental points is defined as 2 raised to the power q minus 1. And here we have 3 ingredients, x1, x2, and x3, such that q will be equal to 3. So if you substitute for q here, then we are going to be having 7 base experimental points. The design points we have to consider in these experiments are the single component blends. And the single component blends are 1, 0, 0, 0, 1, 0, and 0, 0, 1. The next series of points are the binary blends 0.5, 0.50, 0.5, 0.5, 0.5, 0.5. The third series of points, they are the ternary mixtures. And here the ternary mixtures are also similar to the overall centroid because we are dealing just with 3 ingredients. And so the ternary mixtures, which also equal to the overall centroid, will be equal to 1 over 3, 1 over 3, and 1 over 3. And with that, we are going to have our experimental design table with 7 runs. Sometimes we extend this design into a mixture centroid augmented design. This involves adding more experimental points like the axial blends or the interior checkpoints to better estimate interaction effects and improve model fitting. It is especially useful when the mixture's behavior isn't linear. So here, these are our check blends for our augmented points in our design for the 3 component mixture. Here, if x1 equal to 100%, and at the center we have 1/3 of x1, it means that here the value for x1 will be equal to 2 over 3. And here the value for x2 will be 2 over 3, while the value for x3 here will be 2 over 3. So if we choose to experiment at this point where the value of x3 is equal to 2 over 3, then the value of x1 here will be equal to 1 over 6, and the value of x2 at that point will also be 1 over 6 for x3 to be 2 over 3. Remember that the sum of component proportion must always sum up to 100. And that is that for a mixture centroid augmented design. If we augment our base mixture centroid design into a mixture centroid augmented design, then we are going to have 10 experimental design points with 3 extra experimental runs to help explain curvature within the design domain. And again, these points are given in pseudo values, and we can always transform these pseudo values to the real values using this equation. If you found this helpful, don't forget to like, subscribe, and drop comments if you have any doubts or if you need any clarification. Thanks a lot for watching, and see you in our next video.